Right now, somewhere on this planet, a satellite is hurtling through low Earth orbit at 17,000 miles per hour, and the only reason it stays on course is a string of numbers that a computer recalculates 60 times per second. Every stock trade on Wall Street, every text message between continents, every heartbeat tracked on a hospital monitor, all of it runs on a counting system that humans invented. But we didn't always have numbers. For most of our existence as a species, we had no way to count past what we could see with our own eyes. That was roughly 300,000 years of human history with no numbers at all. Then, on a mountainside in southern Africa, someone picked up a baboon bone and scratched a line into it. That simple scratch changed everything. The border cave sits in the Lebombo Mountains along the border of South Africa and Eswatini, a shallow opening in a cliff face surrounded by dry grass and red earth. In 1970, archaeologists working inside that cave pulled a small, dark bone fragment from the sediment. It was the fibula of a baboon, about the length of a pencil, and carved into its surface were 29 parallel notches. They called it the Lebombo bone. Dating put the artifact at roughly 43,000 years old, which made it one of the oldest known mathematical objects on Earth. 43,000 years. That is not a typo. To put that in perspective, the wheel would not be invented for another 38,000 years. Agriculture was still 30,000 years away. The first cities would not appear for another 35,000 years. But somebody in that cave was already counting. Now, you might be wondering what exactly they were counting. And that is the question that has driven archaeologists a little crazy for decades. 29 notches. Some researchers believe it was a lunar calendar, tracking the roughly 29.5-day cycle of the moon. Others think it could have been something simpler, a record of days, or a tally of hunted animals, or something we cannot even guess at because the cultural context is gone forever. The truth is, we do not know. But what we do know is that whoever carved those marks understood something that no other species on the planet has ever figured out. They understood that a mark on a surface could stand for a thing that was not there. A scratch on a bone could mean a day that already passed, or a deer already eaten, or a moon that had not risen yet. That is abstraction, and abstraction is the foundation of everything that comes after. About 20,000 years later, and roughly 3,000 miles north, in the area near Lake Edward, in what is now the Democratic Republic of the Congo, someone carved a different bone. This one came from the same species, a baboon, but the markings were far more complex. The Ishango bone, discovered in 1950 by a Belgian geologist named Jean de Heinzelin, has 3 columns of notches arranged in distinct groups. One column contains groups of 11, 13, 17, and 19. Those are all prime numbers. Another column seems to show a doubling pattern, and the third column has groupings that add up to 60, which has led some mathematicians to suggest it represents a base 60 counting system, thousands of years before the Babylonians supposedly invented one. This is where the story takes a turn nobody expected. Because if the Ishango bone really does show prime number awareness and a base 60 system, then the mathematical sophistication of prehistoric Africa was far more advanced than anyone assumed for most of the 20th century. Jean de Heinzelin himself argued that the bone was evidence of arithmetic knowledge, but plenty of his colleagues pushed back, saying the notches could be decorative, or random, or just a tool for grip. The debate is still not settled. But here is what is not debatable. 20,000 years ago, people in Central Africa were organizing information into patterns, grouping quantities, and recording those patterns on physical objects. They were doing math. They just did not call it that. For thousands of years after the Ishango bone, counting stayed physical. You held pebbles in your hand, you notched a stick, you tied knots in a cord. The problem with all of these methods was the same. They worked fine for small numbers, but they fell apart when quantities got large. Try counting 400 sheep with notches on a stick, and you will understand the limitation fast. Counting needed to evolve beyond one mark per thing, and the place where that evolution happened was a flat, sun-baked plain between 2 rivers in the Middle East. Mesopotamia, the land between the Tigris and the Euphrates, In modern-day Iraq, around 8000 BCE, long before anyone there could read or write, the people of this region started using small clay objects to keep track of goods. These were tiny, simple shapes. A cone meant a small measure of grain. A sphere meant a larger measure. A cylinder meant an animal. Archaeologists have found thousands of these tokens scattered across dozens of sites, from Turkey to Iran, tucked into storage rooms, buried in temple floors, and mixed into the rubble of ancient market stalls. They were the world's first accounting system, and they worked remarkably well for a society that was just beginning to settle into permanent farming villages along the river valleys of Mesopotamia. But here is the detail that everyone missed at the time. Those clay tokens were not just record-keeping tools, they were the seeds of writing itself. Around 3500 BCE, something changed. Merchants and temple administrators in the Sumerian city of Uruk started placing groups of tokens inside hollow clay balls called bullae. You seal the tokens inside, and then you press the shapes into the wet surface of the ball before it dries so that you can see what is inside without breaking it open. Think about that for a second. The impression on the outside made the actual tokens inside redundant. You did not need the physical objects anymore. The marks on the surface carried the information. Within a few centuries, people stopped making tokens altogether and just pressed symbols directly into flat clay tablets. Those symbols became cuneiform, and cuneiform became the first writing system in human history. So counting did not just come before writing. Counting literally invented writing. The Sumerian scribes in the temple complexes of Uruk and Ur carved wedge-shaped marks into wet clay with a cut reed stylus. And they developed separate symbols for 1, 10, and 60. Their system was powerful enough to record harvests, debts, land boundaries, and wages across an empire that stretched from the Persian Gulf to the mountains of eastern Turkey. They could add and subtract. They could divide rations among workers. They could calculate the area of a field. But their system had a weakness that would haunt civilization for millennia, and we will get to that in a moment. First, you need to see what was happening along the Nile River at roughly the same time. The Egyptians built their own number system using hieroglyphic symbols. A single vertical stroke meant 1. A heel bone shape meant 10. A coiled rope meant 100. A lotus flower meant 1,000. A bent finger meant 10,000. A tadpole, or maybe a frog, meant 100,000. And a seated figure with raised arms, sometimes interpreted as a god, meant 1 million. The system was additive, meaning you simply repeated the symbol as many times as you needed. To write 342, you would draw 3 coiled ropes, 4 heel bones, and 2 vertical strokes. Clean, logical, and beautifully illustrated on the limestone walls of temples along the Nile Valley. The Egyptians put their numbers to astonishing use. The Great Pyramid at Giza contains roughly 2.3 million stone blocks, each weighing an average of 2.5 tons, assembled with a precision that still impresses structural engineers today. Building something like that requires calculations for volume, slope, labor allocation, material transport, and food distribution for tens of thousands of workers over decades. The scribes who managed those calculations did it all with an additive system and no concept of place value. We know exactly how sophisticated their arithmetic was because of a single papyrus scroll bought by a Scottish antiquarian named Alexander Henry Rind from a street vendor in Luxor in 1858. The Rind papyrus, now in the British Museum in London, dates to around 1650 BCE and contains 84 worked mathematical problems covering everything from dividing bread rations among workers to calculating the volume of a cylindrical granary. It is essentially a textbook, complete with reference tables and step-by-step solutions. The scribe who wrote it was not inventing new math. He was teaching established methods that had already been in use for centuries. Egyptian arithmetic was old, tested, and deeply embedded in the functioning of the state. But additive systems have a ceiling. Try multiplying 2 large numbers using Egyptian hieroglyphs, and you will quickly see the problem. The notation gets enormous. Writing the number 999,999 in Egyptian hieroglyphs would require 54 individual symbols. That is not a number system built for complex arithmetic. It is a number system built for record keeping, and it worked brilliantly for that purpose, but it could not scale. Meanwhile, back in Mesopotamia, the Babylonians were pushing in a different direction entirely. They had inherited the Sumerian base 60 counting system and refined it into something genuinely sophisticated. Using just two symbols, a vertical wedge for 1 and a corner wedge for 10, they built a positional system where the value of a symbol depended on where it sat in the sequence. The same vertical wedge could mean 1, or 60, or 3,600, depending on its position. This was a massive leap. Positional notation meant you could represent enormous numbers with just a handful of symbols. And the Babylonians used this power to do things that still echo in your daily life. 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. Those numbers are not arbitrary. They come directly from the Babylonian base 60 system, which spread through the ancient world via astronomy and trade, and embedded itself so deeply into human culture that we still use it more than 4,000 years later. Babylonian astronomers on the ziggurats of cities like Babylon and Nineveh tracked the movements of planets across the night sky with a precision that European astronomers would not match until the Renaissance. They predicted lunar eclipses. They mapped the path of Venus across years of observation. They compiled their findings on thousands of clay tablets that were stored in palace libraries, and some of those tablets survived 3,000 years in the dry soil of Iraq, to be read by modern scholars who were stunned by the accuracy. One particular set of tablets from the city of Sippar contained planetary calculations so precise that they matched computer-generated models to within a few arc minutes. But the Babylonian system had a fatal flaw, and this is the part that explains everything that comes next. They had no zero. When a Babylonian scribe wanted to write the number 60, he would put a single wedge in the 60s column and nothing in the ones column, but nothing looked exactly like a blank space. So the number 60 and the number 1 could look identical depending on context. Sometimes scribes left a slightly wider gap to indicate an empty position, but it was inconsistent and error-prone. Imagine trying to run an empire's finances when 3,660 and 1 can all be confused for each other, depending on how much space the scribe left between marks on a clay tablet. That is not a minor inconvenience. That is a structural crisis baked into the system itself. This decision seemed small at the time. It was not. The absence of zero was not just a gap in notation. It was a wall that blocked mathematical progress for civilizations across the planet for thousands of years. The Greeks, who inherited much of Babylonian astronomy and geometry, never developed a zero either. Aristotle himself argued that a void, a true nothing, was logically impossible. If nothing exists, then it is not nothing, it is something. Greek philosophy actively resisted the concept, and without zero, Greek mathematics remained geometric, visual, tied to physical space rather than abstract calculation. You could prove that the angles of a triangle add up to 180 degrees, but you could not solve a quadratic equation. The Romans built an empire that spanned from Scotland to Syria, and they did it with a numeral system that could barely handle multiplication. Roman numerals, the system of I, V, X, L, C, D, and M, were additive and subtractive. They had no positional notation and no zero. Try dividing MCM XLIV by XLVI sex using only Roman numerals, and you will understand why Roman merchants used counting boards and abacuses for any serious arithmetic. The numerals were for labeling, for carving into monuments and stamping onto coins. They were a display technology, not a computational one. Pay attention to this pattern because it explains everything. The Greeks had geometry, the Romans had engineering, the Egyptians had architecture. Three of the most accomplished civilizations in human history, and all three of them hit the same wall. Their number systems could record quantities, but they could not easily manipulate them. They could say, This is how much, but they could not efficiently ask, what happens if? Arithmetic stayed slow, laborious, and limited to specialists. If you wanted to multiply two 4-digit numbers, you needed an abacus and training. If you wanted to divide, you needed even more training. The idea that an ordinary person could sit down with a pencil and paper and do long division, that was still more than 1,000 years away. Everything was in place. The world just did not know what everything was building toward. The solution came not from the Mediterranean, not from Mesopotamia, not from the civilization with the biggest army or the tallest monuments. It came from the Indian subcontinent, and it changed the trajectory of human thought more than almost any other single idea. By the 5th century, Indian mathematicians were using a decimal system with 9 symbols and a dot, or sometimes a small circle, to represent an empty place value. But it was Brahmagupta, a mathematician and astronomer working in the city of Bilamala in northwestern India in the 7th century, who wrote down the first known rules for calculating with zero. In his work Brahmasfuta Siddhanta, written around 628, he stated that 0 added to a number leaves the number unchanged, that 0 subtracted from a number leaves the number unchanged, and that a number multiplied by 0 becomes 0. He also attempted to define division by 0, which created complications that mathematicians would wrestle with for centuries afterward. But the key breakthrough was treating 0 not as a philosophical abstraction or a placeholder gap, but as a number in its own right, a quantity, something you could add, subtract, and multiply, just like any other number. Think about what that means. For the first time in human history, nothing became a mathematical object. You could write it, calculate with it, and place it in a sequence of digits where its position changed the meaning of everything around it. The number 100 and the number 10 and the number 1 all use the same digit, a single 1. But they are radically different values because of where the zeros sit. Without 0, positional notation does not work. And without positional notation, you are stuck scratching tally marks on bones, which is essentially what the rest of the world had been doing in increasingly sophisticated ways for 40,000 years. The Bakhshali manuscript, discovered in 1881 in what is now Pakistan, contains some of the earliest written examples of the 0 symbol used in calculations. Carbon dating has placed portions of the manuscript as early as the 3rd or 4th century, which would make Indian 0 even older than Brahmagupta's formal rules. The manuscript shows arithmetic operations, fractions, and algebraic equations worked out with a dot representing 0. It is a working document, not a philosophical treatise. Whoever wrote it was solving practical, everyday problems, merchant calculations, land measurements, tax assessments, and profit distributions, using a number system that the rest of the world had not yet imagined. Now, a number system is only useful if people actually use it. And for Indian numerals to change the world, they needed to travel. The vehicle for that journey was the Islamic Golden Age, and the engine was a single institution in the city of Baghdad. By the late 8th century, the Abbasid Caliphate controlled territory from North Africa to the borders of China. Caliph Harun al-Rashid and his son al-Mamun established the House of Wisdom, a vast library and translation center in Baghdad that brought together scholars from across the known world. Hindu texts, Greek philosophy, Persian astronomy, and Chinese papermaking technology all flowed into this institution and mixed in ways that produced entirely new fields of knowledge. One of those scholars was Muhammad ibn Musa al-Khwarizmi, a mathematician and astronomer who worked at the House of Wisdom in the early 9th century. Around 820, he wrote a book whose Arabic title roughly translates to The Compendious Book on Calculation by Completion and Balancing. That book introduced systematic methods for solving equations by manipulating both sides to isolate the unknown quantity. The Arabic word for completion in the title, al-jab, became the English word algebra, and al-Khwarizmi's Latinized name became the word algorithm, the step-by-step procedures that run every piece of software on every computer on the planet today. But al-Khwarizmi did something else that was arguably even more important. He wrote a separate treatise explaining the Indian numeral system, including zero and positional notation, and he demonstrated how to use it for practical arithmetic. His work made the case that this system was faster, more compact, and more versatile than anything the Arab world, the Greek world, or the Roman world had ever used. Merchants could do in their heads what used to require a counting board. Astronomers could calculate planetary positions with fewer errors. Tax collectors could audit accounts in a fraction of the time. The numbers were not just better, they were a different kind of tool entirely. From Baghdad, the Hindu-Arabic numeral system spread west across North Africa, through the great learning centers of Cairo and Fez and Cordoba, and east along the Silk Road trading routes through Central Asia to the borders of China. Wherever it went, it displaced older systems, not through conquest or decree, but because it worked. Merchants adopted it because it made their businesses run faster. Astronomers adopted it because it made their calculations more accurate. Administrators adopted it because it made their records cleaner. But Europe was a holdout. When the Hindu-Arabic numerals first reached the Christian kingdoms of Western Europe in the 10th century, they were viewed with suspicion. The Roman numeral system was familiar, traditional, and deeply embedded in legal and commercial practice. Merchants who had spent their careers mastering the abacus did not want to learn a new system. Church officials distrusted anything associated with Arab or Islamic culture, and the general public simply did not see the need for change. Then, in 1202, a young Italian mathematician named Leonardo of Pisa published a book that cracked the door open. His father was a customs official in the North African port city of Bugia, and Leonardo had grown up watching Arab merchants calculate with a speed and elegance that left European traders in the dust. He learned the Hindu-Arabic system from Arab tutors and traveled across the Mediterranean, studying mathematics in Egypt, Syria, Greece, and Sicily. His book, Liber Abaci, meaning Book of Calculation, was written in Latin and ran to hundreds of pages. It introduced the Hindu-Arabic numeral system to a European audience using practical commercial examples that merchants could immediately apply in the trading ports and counting houses of the Mediterranean. He showed how to convert currencies, calculate interest, divide profits among partners, and measure goods, all using 9 digits and a 0 instead of the cumbersome Roman numeral system that European commerce had been struggling with for centuries. The response was not instant adoption. It was fierce resistance followed by slow surrender. The city of Florence actually banned Hindu-Arabic numerals in official banking documents in 1299, worried that the unfamiliar symbols could be easily altered to commit fraud. A 1 could become a 7. A 0 could be added to inflate a figure tenfold. The old Roman system, where values were locked into letter shapes, seemed safer to the bankers of Florence, which, looking back, was either incredibly cautious or incredibly short-sighted, depending on your perspective. But the new numbers kept spreading anyway, driven by a force stronger than any law: efficiency. A merchant in Venice who could calculate exchange rates in his head using Hindu-Arabic numerals had a real advantage over a competitor fumbling with an abacus and Roman numeral accounting ledgers. Double-entry bookkeeping, the system that made modern finance possible, became far more practical with positional numerals. The trading houses of Venice and Genoa adopted the new numbers for private accounts even while public records stuck with Roman numerals. Bankers started keeping 2 sets of books, one in the old system for the authorities and one in the new system for actual business. Mathematicians across Europe began publishing textbooks explaining the new system. The printing press, arriving in the mid-1400s with Gutenberg's workshop in Mainz, accelerated the process by making those arithmetic textbooks cheap and widely available across Western Europe. By the 1500s, the Hindu-Arabic system had effectively won. Roman numerals survived on clock faces, movie credits, and monument inscriptions, decorative echoes of an ancient system that could no longer keep up with the demands of a world that was beginning to count faster, count higher, and count more precisely than ever before. And then came the real payoff, the moment when counting stopped being a record of the past and became a tool for building the future. Once you have positional notation with 0, you can do something that no previous number system allowed. You can count in base 2, ones and zeros, on and off, true and false, binary. In 1679, the German mathematician Gottfried Wilhelm Leibniz described a complete binary number system in a paper that laid the theoretical groundwork for digital computation. Leibniz was fascinated by the elegance of it. You could represent any number, no matter how large, using only 2 digits. He saw in it a kind of mathematical perfection, a reflection of creation itself, everything from nothing, 1 from 0. He even sent his binary system to Jesuit missionaries in China, hoping it would impress the Chinese emperor. It did not, but the math was sound, and 2.5 centuries later, it would prove to be the most consequential number system ever devised. He did not have a machine to run it on. That would take another 260 years, but the math was ready. And when the first electronic computers flickered to life in the 1940s, every circuit, every transistor, every logic gate operated on the same principle that Leibniz had described, and that Indian mathematicians had made possible 1,000 years before him. A number is defined by its position, and a position can hold one of 2 states, a 1 or a 0. And here we are, your smartphone, the one probably sitting in your hand right now, processes billions of binary operations per second. The GPS satellites orbiting overhead calculate your position using triangulated timing signals measured in nanoseconds, all represented in binary. The global financial system moves trillions of dollars per day through networks that encode every transaction as strings of ones and zeros. The internet, the power grid, air traffic control, medical imaging, weather forecasting, every piece of modern infrastructure sits on top of a counting system that traces an unbroken line back to those 29 notches on a baboon bone in a cave in the Lebombo Mountains. We tend to think of civilization as being built by great leaders, great armies, great monuments, and those things matter. But underneath all of them, underneath the pyramids and the aqueducts and the cathedrals and the space stations, there is something quieter and more fundamental. The ability to take a quantity, represent it with a symbol, and manipulate that symbol to discover something new. Counting is not glamorous. It does not show up in paintings of great battles or epic poems about heroes, but it is the silent engine behind everything. Every wall that stays standing required someone to calculate the load it would bear. Every ship that crossed an ocean required someone to calculate the angle of the stars. Every vaccine that saved a life required someone to calculate the dosage. The marks that built civilization were not words. They were numbers. And the story of how we learned to make those marks, from scratched bone to clay tablet to ink on parchment to light on a screen, is the story of how we became the species that could imagine a future and then count our way toward it. If this video changed the way you think about something as simple as counting, subscribe to the channel and leave a comment telling us which part of this story surprised you the most. And if you know someone who loves history or math or both, send them this video so they can see it too.